Hello everyone, welcome to my channel. Today I'd like to discuss the topic of Fortinet SD-WAN with you. SD-WAN has been a very popular WAN network solution in recent years, and Fortinet has always been a leader in this field. It first introduced SD-WAN capabilities in its 6.2 version in 2019, and it has been over 4 years now, with multiple versions being iterated and updated. The product's features have become very comprehensive and mature. So, today I want to share my understanding of SD-WAN from my perspective, hoping it will be helpful to everyone. First, let's look at what exactly SD-WAN is. SD-WAN stands for Software Defined Wide Area Network, meaning it uses software methods to dynamically control WAN network traffic. This control can be based on protocols or services, or it can be based on applications. Simply put, let's say I have a firewall with SD-WAN capabilities installed in my office, and for safety, I applied for 2 broadband connections, one from telecom and one from Unicom. First, I can define a rule based on protocol or service. I route all HTTPS traffic going to the public network through the telecom broadband. Then, other voice traffic, such as SIP protocol traffic, I route through the second Unicom broadband. If you say I have an application like TikTok or Zoom, and I don't know its specific protocol or port number, that's not a problem. I can create a rule based on the application, because on Botigator, there is a ready-made ISDB. All I have to do is select the appropriate application, and then I can dynamically create a rule, for example, for social network protocols like TikTok, Bilibila, or Facebook. I can have them use the first broadband from telecom. For other applications used in my office, such as Zoom or Teams, I can have them use the second broadband, thereby enhancing the user experience. On this basis, the 2 broadband connections can also back each other up. For example, under normal circumstances, I can choose the telecom broadband as my primary exit. Once its ping value or bandwidth usage reaches a certain threshold, I can switch some of the traffic to the second Unicom broadband. The above is what is meant by software-defined methods to control WAN network traffic. Simply controlling traffic is not enough. We know that a big selling point of SD-WAN is that we can use existing public broadband to replace dedicated networks. So, to achieve this, some security assurances are needed. We know that typically, if running a site-to-site VPN over the public internet, we usually rely on IPsec technology. Fortinet has made some optimizations to traditional IPsec VPNs, introducing a concept called AD-VPN, which stands for Auto Discovery VPN. How do we understand Auto Discovery VPN? Actually, here, we could draw a simple site-to-site VPN network topology. At the top is a hub site, which is the central point of the entire VPN. And then below we have 2 spokes, spoke 1 and spoke 2. In a traditional VPN network, it's generally the case that I run an IGP protocol between these 3 sites, and the hub acts as a route reflector, reflecting routes between the 2 sites. So, if I, from S1, want to access S2, typically the traffic first goes to the hub, and then the hub forwards the traffic to spoke 2. AD-VPN optimizes this process by, for example, when S1 wants to access S2, the first packet is still sent to the hub. Firstly, the packet, it will still be directed to the hub. Here, the hub site does not just simply forward the packet, because we know the hub is simultaneously establishing IPsec tunnels with both S1 and S2. It is aware of the public addresses of both sites at the same time. So when it receives a packet from S1, it sends back a shortcut offer, meaning it tells S1, I have S2's address. Why don't you 2 communicate directly? Then, upon receiving this offer message, S1 will attempt to establish a direct connection with S2, a temporary IPsec tunnel. From the second packet onwards, all subsequent packets will be sent directly through this temporary tunnel, thus saving on traffic and reducing network latency. This is what is called AD-VPN. So through the 2 points we've described, one is software-defined control of WAN traffic, And the other is what I just mentioned, including AD-VPN and other features of next-generation firewalls. South Dakota, WAN can indeed help us improve the utilization of the entire WAN link and enhance the user experience. At the same time, because of the existence of AD-VPN, ordinary home broadband can completely meet our requirements for security and availability. Having said so much, if you carefully review the features we've just discussed, you will realize that SD-WAN is not really a brand new technology, but rather it is a repackaging and improvement of existing technologies, thus forming a new type of solution. So, from my understanding, I think SD-WAN is actually very simple. It only consists of two parts, which, in my view, makes it very straightforward. It is composed of just two elements. The first part is essentially about traffic control, which is really just policy routing, and the second part is actually about pairing it with some features of next-generation firewalls, thus forming the SD-WAN solution. And the core of this is still policy routing. Once you understand the core logic of policy routing, you can quickly grasp SD-WAN. The rest just requires some practical experience for you to master some of the configuration details. So this video focuses primarily on routing to explain the logic of SD-WAN path selection. Routing, I believe, is already familiar to everyone. So here, I just want to quickly go over some routing concepts related to SD-WAN. Here, I have a flowchart of routing lookup on a FortiGate firewall. So how do we understand this flowchart? We can start by dividing the flowchart into two parts. How to understand this flowchart? First, let's look at the lower half of the diagram. First, let's look at the bottom part of this chart. When we talk about routing, we think of routing protocols and the routing tables generated by these protocols. Routing tables are a concept at the control level. Speaking of actual data forwarding, routing tables generally need to be mapped again to map into the data plane's forwarding information base, FIB, which is the data forwarding table. When a packet passes through the router, it queries this routing forwarding table, thus determining the final output interface for the packet. For the Linux operating system, we usually have a concept called routing cache, meaning that once the forwarding table lookup is complete, the results of the lookup are stored in this routing cache. So when the next packet from the same data stream arrives at our router, it no longer needs to query the forwarding table and can directly forward the packet, thus improving the efficiency of data forwarding. With this specific data forwarding logic in place, we can then perform some logical operations on this basis, which brings us to the upper part of our diagram. Specifically, for the FortiGate firewall, all these policies can be divided into three parts. The first part, which has the highest priority, is the regular policy routing. The second part includes some routing information carried by ISDB. The third part, which is our focus, is the routing information related to SD-WAN. When a packet arrives at the firewall, it is basically matched in a top-down order. You might ask, this is a top-down flowchart. Why do you need to split it into two parts to explain? This involves a problem we will discuss later, which is an issue with the data transformation table validation. We know that policy routing is an operation we perform at the logical or control layer, but whether the actual path of the data packet can go through still specifically depends on whether my data transformation table contains the path you specified. This is why we perform data transformation table validation here. It's like saying, I want to drive from Beijing to Shanghai. I know there are highways 1, 2, and 3, all of which I can take, but I'm not sure which one is the best. So at that moment, I could randomly ask someone on the street to just pick one for me, and any of them would be fine. But if you were to tell me about a fourth highway, I would definitely know you were making it up, because that route doesn't exist at all, and I definitely couldn't take it. So, applying this to our data forwarding aspect, we also need to go through a verification process to ensure that packets can travel along a true path and ultimately reach their final destination. Typically, there are three logical verifications. to ensure data packets can proceed along a real path. Normally, these verifications involve three types of logic. The first is that I verify both the output interface and the gateway address. The second is that I only verify the output interface. And the third is that I only verify the gateway, not the output interface. Now, let's use a simple example to understand how this flowchart operates. On the left is an example of a forwarding table, which consists of three parts. The first is the destination address, the second is the gateway address, and the third is the output interface. On the right, correspondingly, we have 4 policy routes. Let's first verify these 4 policy routes one by one, starting with the first policy route. The first policy route targets addresses in the 172.16, 0.0/16 range, which corresponds to the third entry in the left forwarding table. Next, we verify its output interface is ETH0, and its gateway address is also 192.168.1.2, which matches the entry on the left. So we can confirm that the first policy route is a feasible one. Correspondingly, the second and third ones can be seen. The second has the corresponding output interface, and the third has the corresponding gateway address. So we can confirm that the second and third policy routes are also valid. Now coming to the last policy route. The last policy route targets the January 3rd 10, 024th address. And comparing with the left forwarding table, we find there is no matching specific route. So we have to use the last default forwarding table entry as an alternative. Then further, comparing the output interface and gateway address, we find that neither the interface nor the gateway address matches. Thus, we know this last policy route is not a valid one, and we cannot use it for forwarding our packets. That's all for the basic routing concepts related to SD-WAN we've discussed. Now, let's look at the rule and what the selection rules for it are. So, in the top left corner is the actual rule. At first glance, everyone might notice this actually resembles policy routing almost exactly. The only difference here is in the destination. It not only configures some addresses as objects, it can also select specific service types or application types as targets to match traffic. And the order of rule matching is generally from top to bottom, similar to how firewall rules are matched. So if any rule matches, the packet will be accordingly forwarded. And this ends the routing decision process for this packet, usually at the end of all manually configured rules. There's an implicit default rule. This rule is typically there to catch traffic not matched by previous rules. Typically, this implicit rule involves some form of load balancing. I remember there being 5 different choices, which allow all packets to be load balanced across SD-WAN ports. Now let's take a look at the specific process of routing lookup. As previously stated, all rules are queried from top to bottom until the last rule is queried, and if no match is found, then it will match this implicit rule. During each rule's matching process, there are 2 situations or configurations we can choose from. This relates to the forwarding table validation I mentioned earlier. Let's first look at the default situation. Under default settings, I need to perform forwarding table validation. So, for example, if this packet has already reached the firewall, first, I'll match it against the first rule. The first thing I need to do is to perform a lookup in the FIB. And through this lookup, I might find out that after the query, I can determine the FIB will return to me an output interface, for instance. The returned output interface is ETH0. First, I will verify whether ETH0 is an SD-WAN member, meaning whether this interface can be used to forward SD-WAN traffic. If the result is no, it means the actual forwarding is unrelated to SD-WAN, then I would skip this route. But if after my query I find out this output interface is an SD-WAN member, then I will proceed with the following verification. Next, this verification is called the output interface list verification. What is an output interface list? We know each rule can be configured with a corresponding output interface. This output interface can be a single interface, or it can be multiple interfaces. In the case of multiple interfaces, the firewall will ultimately choose the best among them. The one with the highest priority or the lowest latency will be used as the output interface. So the so-called output interface verification means that based on the interface returned by the FIB, I will compare it with the list of output interfaces. If the interface returned by the FIB is in the configured list of output interfaces, I can be sure all information tells me this rule can be used to forward the data entry. Next, I will proceed based on additional criteria, such as SLA configurations, to select the best interface for interface selection based on SLA configurations, and then finally forwards the data packet. For instance, in the example I previously mentioned, the output interface I returned is ETH0, but in the list of configured output interfaces, there's only spoke 2, so they do not match. Then, unfortunately, I know that this rule cannot be used to forward this current packet, and then the next rule will be validated. So this is the standard rule domain packet forwarding validation process. Okay, someone might say, this process is too cumbersome. Can I skip this FIB validation? The answer is yes, but there's something you need to be aware of. The configuration I am presenting here is meant for an individual rule. For instance, if you want to skip FIB validation for all rules, you need to enable the default and gateway options for each route, so that when you query each rule, you will not perform FIB table validation. Someone might ask again, is this configuration to skip FIB validation really encountered in regular work? The answer is definitely, especially when designing multi-site side-by-side VPNs. We often choose to send default routes from the hub to various spoke sites. Thus, from the perspective of spoke sites, my routing table is also very concise, which simplifies network management. And during the configuration process, I don't need to manually distribute new network segments each time they appear. However, for SD-WAN rules, the absence of specific routes could mean that during the FIB validation process, mismatches may occur, which could prevent traffic from being forwarded as intended. So at this time, we can see that configuring rules is a process that requires comprehensive consideration. While ensuring that the routing table is both concise and complete, we also hope that the configuration of rules is not too complex. Otherwise, it might somewhat defeat the purpose of policy routing. Skipping the FIB table check in this setting provides us a method or a transitional means to achieve our desired effects with relatively few rules. Up to this point, the core content of rule selection logic has been thoroughly discussed. Next, as the final part of this theoretical discussion, I want to further explore the topic of SD-WAN. This part relates to locally originated traffic moving forward. As the last part of this theoretical course, I would like to continue to expand on the topic of SD-WAN. This part will discuss issues related to locally originated traffic, which is an interesting issue we encountered when we first started using SD-WAN. At the beginning of using SD-WAN, we noticed that almost all firewalls, including their locally originated traffic, such as from the firewall to the Fortinet manager, or the DNS requests originating from the firewall itself, they always end up being forwarded to the wrong port. After investigating, we discovered that all of the rules we had previously set up were actually only for local traffic forwarding. If it is traffic originating locally, then by default it does not use a rule, but instead uses the default routing table for forwarding. For instance, here, no matter how many rules you configure, even if you skip the FIB check, in the end, it still won't forward our locally originated traffic to the correct port. The solution is quite simple. FortiGate has already integrated these related settings. For example, let's look at this final configuration for the Fortinet manager. Under default conditions, its port selection method is automatic, which is to use the default routing table method. We can manually configure the FortiGate to use SD-WAN rules to forward the relevant locally originated traffic. In the latest versions, for the pin and trace route commands, FortiGate has also added a configuration to use SD-WAN for routing packets, making it very convenient. That concludes the theoretical part of my video today. I have also prepared a simple experiment to demonstrate some of the SD-WAN features I've discussed previously. But considering the length of this video, I plan to put this experimental part in another video, which will make it more convenient for everyone to watch separately. Also, regarding the textual material cited in my video, I will place the links in the video description. Feel free to click and view them. Alright, that's it for today's video. If you have any questions, feel free to leave me a comment below. I also wish everyone an early Happy New Year here, Happy New Year, and best wishes for everything.